Okay, this is the second half. I'm sorry I didn't get the first half recorded. I hope you can pick it up. Second half of section 4.3. And we need everybody's eyes on page 209. Do you remember what we finished up yesterday? We did that graph underneath your post-it.
Yes.
Remember creating that, having to consider things like increasing and decreasing as well as inflection points, slopes of the slope. Remember, to get it proper. Okay, there is a discussion below that example between example 4 and example 5. It's really important, but not very hard. That's always a good combination. Something that's really important, but it's not very hard to understand. And in order to discuss it with you, I want to first discuss the first derivative test. We've used it a lot, only we haven't called it that. So let me remind you how the first derivative test goes. Just try to listen for a minute, and if what I say doesn't make sense, I'll demonstrate one for you on the board. So just try to hear me. So I don't have to put something up here. First derivative test says that if you find the first derivative, then you find where that derivative is equal to 0 and also where it's undefined. Right? We've practiced that in section 4.2. Then you put that on a number line, those points. Those are places, those are critical values, we call them. Critical values, and you check your derivative value in each one of the sections locked off by those zeros or undefineds. Right? And if there is a sign change, as you jump across one of those critical values, if there is a sign change, then there is a max or a min at those critical values. Is that true? Okay. And if there is no sign change as you jump across one of those critical values, what does that mean? There's a shelf point there. It means it continues to go up, it just flattened out for a minute. Okay? Or it's even possible if there's no sign change across an undefined point, that's one of your critical values. If it's an undefined point and there's no sign change in which you jump across that, it could mean there's a vertical tangent shelf, a sideways shelf there.
Right. Oh, yeah.
But it could still continue to go up. Now, do you need me to demonstrate that?
No.
Everybody understand the first derivative test?
I'm a little confused with those vertical shelves. Oh, what? Jose. Right here.
Nicely done, Sam. You okay with that?
Yes.
See, just to reiterate for those watching this, if we have a vertical tangent someplace, so this is the actual graph of the function. It comes up like this, becomes vertical for a second and continues up. Can you see that this thing is increasing all the time?
Yeah.
Which means that the slope of this line and the slope of this line after the critical value, which is right there, are both positive. So you won't see a sign change across this critical value where it was undefined. And the reason for it is because the shelf point is a vertical shelf instead of a horizontal one, which looks like this. You see what I'm saying? The shelf point here is flat, like a shelf. But this shelf has been laid on its side.
It's a wall point.
So this, right, it's a wall point. You want to call it that, it's fine. This right here would be a critical value, but there's no sign change from left to right. They're both positive, goes positive, positive. But this would be because this critical value is a 0. This would be a critical value also in this graph, but it's because it's undefined here. Still, it goes from positive to positive as you jump across it. So we have a type of a shelf point or a wall point, if you want. Okay, everybody clear? Exactly the same thing is true when you do a second derivative test. And that's what this is saying here on page 209. So try to relate the two together. Here's what it says. Caution. It is tempting to oversimplify a point of inflection as a point where the second derivative is 0. That's only about a fourth of the story. That can be wrong for 2 reasons. And they give a couple of examples. The second derivative can be 0 at a non-inflection point. There's no sign change. Take a look at that graph just to the left of that number 1 we're talking about. That graph right there is concave up all the time, isn't it? Which means there can be no inflection point. And yet, the second derivative is 0 at 0. But there's no sign change. So there is no inflection point there. Yeah.
What's the inflection point again?
It's a place where it changes from concave up to concave down, or vice versa. It's a concavity change. And there is no concavity change in this. It's always up, and yet there is the second derivative is 0. as 0. But because there's no sign change in the second derivative across the 0, that is not an inflection point. Just like if there's no sign change in the first derivative, there is no max or min. It's a shelf point of some kind, if there's no sign change. So that can be a problem. So if there's no sign change, there's no inflection point. Also, if it's undefined at a certain location, this I'm talking second derivative. So we're talking about the undefined thing. The concavity, it could be that there's no inflection point because of a vertical tangent. The second derivative need not be 0. Oh, the second derivative doesn't have to be 0 to find an inflection point. It has to, you also have to consider undefined as well. Okay? Undefined is like in a vertical tangent. There is a change in concavity in this graph. That's one he was showing. There is a change in concavity in this graph. Goes from concave up to concave down, but the place where it changes is not some place where the second derivative is defined. It is a critical value because it's where the second derivative is 0. So, it's where the second derivative is undefined. Do you want to look at that one a little closer? Anybody? You do? Okay, so consider this point. The first one failed because there was no sign change across the critical value of the second derivative. Did you absorb those words? Even though I said them fast? The second case fails because it's not where it's 0, it's at another location where something else happened. So we're going to consider that function. I'll show you what happens. Yeah, the original function f of x is the cube root of x. So I'm going to write it like this. Y prime then will be what? Which is 1 over 3 x to the 2/3, right? Mm-hmm. What's the second derivative? You can use this one.
Negative 2/9.
Good.
Minus x negative 5/3.
Good. Which is the same thing as negative 2 over 9x to the negative 5/3. Right? So when we're looking, if we have the second derivative, when we're looking for inflection points, we're looking for where this second derivative is equal to 0, which it'll never be. This numerator can never be 0. Or where it's undefined, it will be undefined when x equals 0. So if we were to do a second derivative test, we would put 0 as a critical value, and we would check to see if there's a sign change across that. Not that the second derivative is 0 there, but it's undefined there. And so the second derivative's value to the left of 0 would be a negative number raised to the negative 5/3. Let's see if we can analyze that.
Wait, so we're looking for points of inflection, right?
Points of inflection.
How would
So-
positive now move down, right?
That by definition of a point of inflection, a point where the graphic function has a tangent line and where the concavity changes. This wouldn't have, I guess, a vertical tangent line. Is that
Yeah,
still a
that's
tangent
what
line?
we're considering here. You can get changes in concavity with a vertical tangent where the second derivative is
So
undefined.
normally we won't define the derivative with a vertical tangent, but it still technically counts as a tangent. It's still a tangent line. So
Yes.
by the point of
Yes.
definition.
Geometrically speaking. Yep. But the slope of that tangent line is undefined, so we say that that's where the functions or the derivatives are undefined. Okay? So it's undefined at 0. What happens to the left of 0? If you put x is a negative number over here, if x is a negative number, what does this turn out to be? It turns out to be negative. That's always negative. Over, what's a negative number raised to the negative 5/3? Is that positive or negative?
It's negative. Positive power.
What's
It's
that?
negative.
What did you say?
It'd be positive 5/3.
It's positive 5/3.
A negative number raised to the negative 5/3
No,
would be,
it's raised to the positive.
It's on the, we took it down, so it gets to the negative.
oh, yes.
But it's still a negative number.
Still a negative.
Yes, yes. A negative number raised to the 5/3 is still negative because you're cube rooting, so it remains negative.
Yeah.
So this is a negative number times 9 is negative, so this is positive.
Wait, but would it change if it was to the 2/3? Wouldn't it be positive if it was 2/3?
X would be squared inside.
Yeah.
Yeah.
So we're cubing it.
So
And then you're
it's
cube rooting it and then squaring it.
I guess the important bit is that we're fitting it.
It's
You're
Because,
fifth powering a negative number.
okay.
yeah, so it stays negative.
So if there's one positive in the power, then it becomes.
If there's an even in the power,
Yes.
it'll turn out positive.
Even if it's just in the.
At all.
But
Either that or
If you
undefined,
wrote that,
because
it
if
would
it's,
be cube root of
Square
x.
root of negative. Or fourth root of negative.
yeah.
That's how you do that.
What?
Jacob?
But we are cube rooting and then fifth powering, which means the signs remain,
What is the other?
because they're odd.
Is that the order or is it the powering and then?
either way, it's odd.
It doesn't
Negative.
matter, it doesn't matter. If there's an even number,
No.
then it's.
That's a good question. What we're saying here is that the the cube root of x to the fifth is exactly the same thing as the cube root of x to the fifth. They are the same thing.
Really?
Yes, they are.
So on the test, do we have to go through that sign chart bit? To
Well,
prove,
convince yourself that what you got is true. I just want to get this concept down, that you have to look, you have to find critical values by setting it equal to 0 and also finding out where it's undefined. Put them all on a number line, and there has to be a sign change for there to be an inflection point. Just like with the first derivative and a max and a min. There has to be a sign change. So I'm trying to establish a sign change. We all agree that this result on the left is positive, so it's concave up there.
Yes.
Okay, now to the right, if I put a positive number in here, to the 5/3 is still positive, right?
Yeah.
Times 9 is still positive, so I get a negative over a positive, which makes it concave down.
Whoa.
Even though right here it was undefined. Why? Because it was a wall point on the original function. But it did change concavity.
What? Wait, a wall point, what do you mean?
People, it got sort of
Shelf point?
But how would that have?
wall point, your
Wall
point.
point.
He coined it wall point.
Because
Wait,
it's vertical
so-
instead of horizontal. My genius knows no bounds.
Miss J,
What?
so how do we know it's concave up? We get it's going down, but we didn't find any values to see if it's
You
getting.
know it's concave up because the second derivative's value in that region is positive.
Yep.
Okay, listen up. The moral of this story is, when you get to the second derivative, don't just set it equal to 0 and look at those places. You gotta also find out where it's undefined, and you've gotta make sure there's a sign change in your sign chart before you can conclude it's an inflection point. This one is. This is an inflection point, because there's a sign change across the undefined value for the second derivative. So that's what that discussion between example 4 and example 5 is all about. Are
If
you with
there
me?
was no change in concavity, it would not be an inflection
No,
point.
if there is no change in sign, there will be no change in concavity, so there's no inflection point.
Wait, calculator says no sign change. So,
Yes. True. Yeah.
Good talk, Jacob.
So
Alright.
if the original
Big
equation was x, let's say, and then your first derivative is 1 and then your second is 0, does that mean that there's no concavity then? Because it's straight.
This is 0 all the time. There is no concavity.
Literally graduate.
There's no change in sign, so there's no change in concavity, and there is no concavity to begin with. This is a line. Yeah. There's no holding anything on. Okay, that's an exception. Not exception. It's just a strange situation. Are you ready? Move on.
Yes.
Please don't turn a page.
Why?
Just don't.
so we don't cheat, Sam.
I want you
Well, I
to
think
think
might have
about
to
this
stick it
yourselves.
over.
But, Jay.
This is what's on the next page, but so is the solution. So I just want you to, I'm just handing this out to you now, and it's big, you can write on it, do whatever you want to help yourself understand it. But this is a part of what's on the next page, but then so is all of the explanation. I don't want you to see that yet.
No.
You don't give me a paper.
This is a really, really interesting thing, and it really does, for most people, it takes a good deal of lengthy concentration to understand what's going on.
I need a paper. Lengthy concentration, I hate this.
Here's the situation. It probably won't be too much of an effort for you, Jacob.
No, you'd be
It
surprised.
might not be an effort for any of you, but it always was for me, and it still is every time I present it. Shh. Example 5 says this. A particle is moving along the x-axis with position function, and it gives you this, x of t. But notice that it is a cubed polynomial, which means that the second derivative will be a slanted line. So this is not like when we did things where the accelerator was gravity. When the accelerator was gravity, a vertical thing, gravity always turned out to be just a constant, which means we started out with a quadratic, right?
This thing's moving all over.
So this thing is going to be, this thing that we're talking about, not only is it not being affected by gravity, as far as doing the problem is concerned, it's moving horizontally, and its function, its motion, its position function is a cubed polynomial, which makes it a little different than what we had before. Now, I did put the functions at the bottom so that we wouldn't have to take the time to take the derivatives of polynomials, because you're good at that by now. So look at the bottom. It says x of t is, and that's what they gave you in this, I've got it written down there, for t greater than or equal to 0. Then the first derivative is what you see there, and the second derivative is what you see there. So we get a cubed function, which is the top one. That's your position function. You with me?
Yeah.
You get a squared function, which is the second one, parabola. That's your first derivative, and the second derivative is a slanted line. Now, before we go on any further, I want to locate some places so that when we talk about it, we're not all talking about things that are close but not the same. So, before we go on any further, I want you to take your papers and mark these. And by the way, for anyone who's viewing this without having a paper, I'm going to show it to you. You can freeze the screen or whatever and copy it down. I don't know, but this is what we're looking at. You can also turn the page and do yourself the disservice of looking at the solution. So that's what we're looking at, okay? All right. Okay. Where would you say that the original function has a point of inflection? We need to agree on this.
2.5.
I don't like 2.5. We could do better than that.
Where the heck?
Okay.
How is 2.5?
2 sevens. 2 fifths. 2 fifths.
I like thirds.
Okay, 1/3.
Why did we look at that one?
I want to know where you believe an inflection point is, and I want to know how you're, because Sam, we're arguing over nitpickies now. Where's he looking to find this value?
Oh, where this equals 0. We're gonna find it. That's how you
Where the second derivative is equal to 0. Where does it cross the x-axis? Can we agree that that is 2 1/3?
Yeah.
And we hate 2
Where's the
1/3
ruler?
in calculus, so we'll call it, write that down. Write it down any place on any graph that it seems pertinent.
7/3. Not bad. What are we doing?
Writing down this thing that we've agreed upon, which I actually told you.
Oh. Thanks.
I actually put it on all 3 of my graphs. Does it look like in the first one that at 7/3 there is an inflection point?
Yeah.
A change in concavity. Looks like that's where it happens, right?
Yeah.
And also notice that we have a minimum at 7/3 on the second derivative. Interesting to note, okay? Let's take a look at some of the other ones. What do you want to call the first crossing of the x-axis in the first picture?
First.
What did we say? What place did we say it's at? How far along?
7/3. 2 1/3, which is 7/3.
It is 4/13.
Okay.
Oh, so.
Wow.
However close that is.
It's not 4/13, maybe 13/4.
13/4.
It's 4/13 after you get to 2. So it's 26.
Yeah.
30/13.
30.
Is that close to 7/3?
Which one is this? 'Cause I'm
Yeah,
not
that's
back.
staying close. That's 1/13 off.
Yeah.
Yeah.
So it's, all right, we're going with 7/3 because it's easier to think about that.
Oh, it's not.
4/13. This is
I thought we were
26/13.
still
This is 30/13. He said 7/3, but it's only 13th off. Okay, so we're going with 7/3, okay? All right. Okay, listen up. It looks like, okay, what does it look like the first, we need to agree. Where's the first crossing of the
Oh,
x-axis?
you cheated.
Up in the top graph.
0. Oh, it's a 0.
Let's guess at it. First crossing of the x-axis appears to be at
4/13.
1/3.
1/3. 4/13.
On which graph?
I think, what would be the easiest thing to think of that we can agree on?
1/3.
Okay, I like 1/4, but okay, 1/3, fine. What are we?
Wait, is this? Are we on the first graph now?
First
Oh,
graph,
it is 1.
All right,
first
break out
graph,
the
first
ruler.
crossing of the x-axis. Let's agree that that's 1/3. Write it down.
No,
Give me a second.
It's 1/3. Shut up, Sam. Look,
That's a third.
That is definitely a 4.
3/13.
People, I don't want to get hung up on this. 1/3, move on.
3/13 is
What does the second crossing appear to be?
2. 7/8.
Let's go with 2, okay? Where does the last crossing appear to be? About?
7/8.
I agree. 5.
That actually looks like
5/6. That's not close.
1,
You got
2,
it.
3, 4.
10, 13.
Are you saying 4 and 7/8 then?
Yeah. Or 1/6. Or 5/6.
4 and 7/8.
4 and 7/8.
5/6 13.
Dude.
4 and 7/8.
7/8.
What is that as an improper fraction? 4 and 7/8.
39.
Yes. 36.
39/8. Write it down.
This is what you get.
Where does it appear that the second derivative crosses the x-axis for the first time?
1.
Look at that.
And the second time,
2/3.
3 and 2/3.
3 and 2
which is?
Oh my
Not
God.
11/3.
All right, write it down.
What is that now? 11/3.
Yes.
Yes.
Can I hear Jacob?
And we got the last crossing. Thank goodness. All right. Wow.
That's
Okay.
not my fault.
We're just getting accurate data.
All right, people, listen up. Here we go.
Don't care about Jacob.
Let's see if we can come up with the scenario of an object. I'm going to do the object. Sorry, I'm the object. Okay? And we are going to agree, because I'm telling you, we're agreeing, that on this horizontal line, that right here where this y-axis is on this grid board, that is 0. Those are negative numbers. X negative numbers. Those are positive x numbers. The size of those is arbitrary. Just, we want to go with the motion on this. Now, I'm going to have to turn this way so people can see what's going on, I hope.
That is so dangerous.
Yeah, I know. With my computer, it's pretty dangerous. Okay, so we're agreeing that I am the object and this is the 0 point. Where would you place me to get this project started?
0.
-1.
Yeah.
Yes.
Why is that -1?
Yes.
Look at the position function when we start the clock.
-1.
See the y value? That's my position. The y value is my position. The x value is, or the x-axis is time. Even though I'm moving this direction, that is not the x-axis I'm moving on. It's the y-axis I'm moving on.
Oh, that's right.
I know, it's pretty crazy. That's why it takes
Hold the phone.
some serious concentration.
We know the numbers.
That's my negative.
Oh, it's
What?
It's -5.
It's
Okay,
-5.
yeah,
Oh.
Okay, so this is -5 whatevers.
Yes.
'Cause I gotta have some places to move.
Okay.
So this is -5, and there's my 0 marker right there.
So move forward for the first 2 seconds.
Hang on.
Wait.
I want to know at this point, if we're talking about position, velocity, and acceleration, I want to know right when the clock starts, which direction should I move?
Forward.
Forward for the first second.
Forward. Sorry.
At that point, do I have any velocity?
Yes.
How much? 20 or so. Is it a forward velocity?
Yes, but slowing.
Hang on.
That is acceleration, Jacob.
Sorry.
At this point, right now, right when we start the clock, I am moving forward. I have to be moving forward because position says I'm going towards the positive, right? Velocity says I'm moving forward because it's positive. Am I being accelerated or decelerated? So I'm being slowed. What could cause that? What sort of an accelerator could cause that? Yes.
Gravity.
Friction.
Yeah, gravity's not in this because the motion
Okay.
is
Friction.
parallel to
There's a
that.
Air.
A fan, if you had, a fan could do it.
The hand.
However, I want to have one accelerator that will both accelerate and decelerate me.
A spring.
A spring. A spring is a good thing.
Elastic energy.
So, if I've got a spring attached to the center of my back, or my butt, whatever you want. If I've got a spring attached to me, what I want to know is, right now, when we start the clock, is that spring stretched or compressed?
It's
I
pushing you
think
away.
it's stretched. It's pretty neutral.
It's slowing you down, so it'll be stretched.
Why would you say it's slowing me down?
It's because your acceleration is decreasing.
Because your acceleration is not decreasing, your acceleration
Your
is,
velocity is decreasing.
acceleration is negative.
Yeah, so it's slowing you down, but it's still pushing you forward. So it's pushing you
Not
forward.
pushing me
backwards.
forward right now.
I don't
It's
like a spring.
pushing you.
I don't like a spring. That would be like a sinusoid.
too bad, we're going with the spring.
What do you want, Sam?
Can we put a jetpack on it?
No,
Wait, so if you're moving forward, but you're moving forward slower and slower.
how do you know that?
Because your acceleration, your velocity's
velocity's going down.
Velocity's going down as time goes along, right?
Yeah.
What's happening to acceleration?
It's going up.
It's staying steady.
It's increasing.
Yeah,
So it's increased spring.
So that's what I want to know. Is the spring pushing me forward or holding me back?
It doesn't make sense.
I'm confused.
I
See,
know.
this
That's
is
why this takes severe
This is
concentration.
why I don't like a spring. The spring would be like a sinusoid.
It's gonna
It's definitely, the spring is definitely stretched though.
Why?
Because it's slowing you down.
Because
It's pulling
It's
you
slowing me down,
backwards.
but talk to me about what the spring is. In this scenario, is the spring the creator of velocity, the creator of acceleration, the change of position?
Acceleration.
The spring is associated with the acceleration. Right now, when we start the clock, is the acceleration positive or negative?
Negative.
Which means it's doing what?
Stretch.
Pulling me that way.
Yeah.
Which means it is stretched or compressed? Stretched. So I have stretched it a bit by the time we start the clock.
Yeah.
And I'm working against it. If I go forward some more, that spring's gonna
Pull harder,
stretch some more.
but you're not. It's stretching less, so you're moving backwards.
No, because you are moving forward. So it is stretching more.
It stretches it.
Well, that doesn't make sense.
The acceleration continues to be negative,
But by
It's
less,
all 7/3.
it's going less and less and less.
but it's concave up, down.
What?
The curve is.
the curve is this.
So what?
There's
Well,
why I
because
don't
looking
like
at
it.
position, you're moving forward
And slowing down
and slowing down.
because I'm being decelerated.
But less and
Yes.
less.
But by less and less. As you move forward, you're being decelerated less and less because this negative acceleration is becoming less and less.
This is why a spring would only work on a sinusoid, because your acceleration would still be a sinusoid.
If it were a spring.
Yeah.
Because it's like going up
Yeah.
and down with an accelerator. Yeah.
But we can't use a spring
Okay.
on this because your acceleration is a linear.
Let's deal with that.
Yeah, so just logically, this isn't making sense.
Yeah,
Okay.
that's why we can't use springs.
Go with the negative and positive on the acceleration, and let's continue the discussion and see if we can make this work. Okay.
So with negative, positive on the acceleration. Okay.
So if the acceleration is negative,
Yep.
and the accelerator is a spring, then we will say that
It's
the spring is stretched.
Yes.
Okay. So I'm going to move forward until I'm going to move forward, and it doesn't take me very long until I arrive here. And acceleration at this point should be
Zero.
no, not yet.
It's getting
The
over.
acceleration should be,
Higher.
Higher. It's
Is
pulling
it?
harder.
is it?
It is on the graph,
It is on the graph.
but it should be.
Acceleration is higher.
Yes. Acceleration is getting higher.
Yeah, so you're pulling hard, so, okay, I see.
But still negative.
No.
When you're at zero on the y-axis.
I'm not confused about the spring.
Just continue with me, okay? So I've now reached the 0 point. I mean, we're barely into it. What do
So
we
7
decide?
thirds?
1/3 of a second, 1/3 of a time unit, right?
Oh, that's fine.
All right, and then I continue to go forward about right here until 1 second is reached. Am I still being decelerated?
Yes,
So I'm stretching the
but
spring
it
more.
should be more, but it's less.
What?
Just hang on,
What are you saying?
hang on, hang on.
Hang
Okay,
About this
so what happens at 1 second as far as velocity is concerned?
It stops.
Velocity hits
Velocity
zero,
is-
so you.
What happens to position at 1 second?
You start moving backwards.
We start moving backwards, and velocity changes to negative, which means I'm moving
Backwards.
left, and am I still being decelerated?
Yes,
Because the spring is still stretched.
but your acceleration should
See,
start.
I feel, yeah, because as you're moving backwards, your
All right,
acceleration
just-
is going up.
All right, you're just gonna have to deal with that in your own
She's
way.
still
Just-
fighting against the
Just
spring.
wait,
She's been
we're going backwards until what?
Until the spring starts to compress.
Until
7/3.
When will the spring start to compress? When am I at equilibrium with the spring?
7/3.
At 7/3 of a time unit, whatever that is. Where am I position-wise?
This does not work.
You're
About where you started.
A little bit more.
A bit more than where you started.
Okay,
Another device.
so I'm a little bit farther back than this. Right now, the spring is equilibrium at 7/3 of a time unit, whatever that is.
Yeah.
You with me there?
Yes.
Now, right at that moment, I mean, this is supposed to be fluid, but right at that moment, where am I headed?
You're headed backwards.
We're headed more left, which means I am, okay, which means the spring is being
Compressed. If you're moving
compressed. I'm still moving left, I'm compressing it. The acceleration is positive, which means the spring is compressed. It wants me to go that direction. The spring wants me to go that direction, but I am still moving it backwards and compressing it. Do you see what I'm saying?
Yeah.
Okay. Is the compression force getting greater? I shouldn't say force, but you know what I mean. Is the acceleration getting greater or smaller as I move backwards? Greater. Is that
Greater,
borne out
less and less
on
greater.
the graph?
Yeah.
Yes. Until when?
Nope, it keeps getting greater.
When, it means time. Until when? Am I going backwards till when? 11 thirds. Let's presume I'm at 11 thirds. What's my position at that point?
Negative.
Negative 15, and I started at negative 5, right? So that's about 3 times, yeah, okay. Okay, so right now, I'm going to come to a stop or continue backwards?
Stop.
Continue, come to a stop. I'm being accelerated.
Yes.
Which direction?
Forward.
Forward, so that's what we mean by acceleration as opposed to decelerate. Why am I being accelerated forward at this point, even though I'm still moving backwards for an instant?
The spring is pushing it.
Compression of the spring.
Because I'm compressing the spring and it's pushing me forward, okay? And then I do what? Right after that instant, I
Shoot forward.
shoot forward because
The spring is pushing.
the spring is pushing, but what, according to the graph, tells you I'm moving forward.
Velocity.
Positive velocity, and the change in position is moving up, right? Yeah? I'm going up until I get to equilibrium at about what?
You never reach an
Yeah,
equilibrium.
you just keep going forward.
Just keep going.
Oh, keep going forward forever. Not equilibrium, not equilibrium in the spring.
That's why the spring can't work though.
Right. You're right.
Yeah,
You're right.
I think it would be better if you had a jetpack and you slowly throttled it up.
I think if you just walked and just changed your pace. You're
Something
I'm
has to
moving
be.
back fast now, and then I'm moving.
But because we didn't start out with the acceleration is not constant. Something's got to be. The spring was the best thing I could come up with on this.
Yeah, but
Jetpack possibly.
Wait. So if your acceleration
You're linearly moving.
is this is going slowing down, by less, and then going faster. I'm done.
Here's the main thing I want you to get out of this. I want you to draw, and you don't have to, you can just be free-handed. I want you to draw a vertical line through all of the graphs at 1.
This is hard.
Draw another vertical line at the 11 thirds we decided on, which is where velocity changes.
11 thirds is
And draw a vertical line through the 7 thirds. So that it looks like this if you're following along, those 3 vertical lines. Okay,
those are surprising.
listen to this. Between 1 and 7 thirds, so I'm in the first gaposis there. Actually go from, first of all, go from 0 to 1. That vertical set of stuff right there. Is the velocity positive or negative? Is the acceleration positive or negative?
Negative.
In that range of values, am I speeding up or slowing down? I'm not talking about direction now. I'm talking about speeding up or slowing down. Speed is an absolute value. Speeding up or slowing down? Slowing down. Okay. So we're slowing down in that first thing. Write that down. Slow down. In that first column. In the next column, what is velocity, positive or negative?
Velocity is negative.
Acceleration is positive or negative?
Negative.
Negative. Am I speeding up or slowing down? I'm talking speed here.
Slowing down.
Speeding up.
What interval are we talking about?
Between 1 and 7 thirds.
No, you're still slowing down.
I'm talking speed here, which is an absolute value.
You are slowing down.
You're speeding
up.
Speeding up.
Oh, you're speeding up downward.
Speeding up to the left. Yes. Speeding up to the left would be a good way to say it. But we are speeding up.
Sorry, why? If we were slowing down there.
We're further away from the zero, Jay.
Look at the position curve, it gets steeper. To the left, yes, but steeper.
Yeah,
Okay.
but I'm like, okay.
But Miss J, that's velocity, not speed. So it would be slowing down. Because velocity has direction too.
I'm talking speed. Speed is always positive.
Okay, we'll talk about speed.
So speed,
I want to talk about speed, and that's what we're doing.
yeah, I am.
You don't understand?
I'm
Very
still
lost.
not
I'm
convinced.
trying to like.
Between 1 and 7 thirds seconds. Do you remember where I am? I'm a little bit past this. The spring is stretched. It wants to pull me backwards. And I begin moving backwards. As I move backwards, am I going faster and faster?
Yes.
Then I'm speeding up.
Well, in looking at velocity and acceleration graphs,
The velocity graph.
The velocity is negative.
Yes.
The acceleration is negative,
Jake, you're getting further and further.
and I am
away from Joe.
speeding up to the left.
Speed is absolute value.
What is speed the absolute value of?
Velocity. No.
Okay, I was looking at acceleration the whole
Okay.
time, so that's why I'm.
Oh my
Alright.
God.
Yeah, I'm trying to combine acceleration.
That's what I'm trying to get you to do.
So your
Now
acceleration.
look in
so
the
look at
next,
the two.
look in the next region between 7/3 and 11/3. That next column right there is velocity positive or negative?
Positive.
Positive. No.
What negative?
Positive or negative?
Negative.
Is acceleration positive or negative?
Positive.
Am I speeding up or slowing down?
Slowing down. I don't like this.
In the last region of things that's going on there, is velocity positive or negative?
Positive.
Is acceleration positive or negative?
Positive.
Am I speeding up or slowing down?
Speeding up.
Speeding up. Yes. Here's the moral of the story. This is not all I want you to get out of it. The whole scenario is a good thing to think about. If the sign on velocity and acceleration are the same, you are speeding up. If the sign of velocity and acceleration, it doesn't matter which one's which, are different, you are slowing down.
It makes sense because they.
They're opposing each other. You must be reducing your speed because of it. Speed, I'm talking about.
Speed.
Direction is not in this. I'm talking about speeding up or slowing
I
down.
don't like this.
So, if acceleration and velocity have the same sign, speeding up. Different signs, slowing down. I need you to understand that because it can help you answer questions and a lot faster if you understand that fact. Okay, now turn the page, and he does a similar thing with sign charts. You can see how they line up or don't line up. Any place where it's pink and pink, you're slowing down. No, speeding up, sorry. Any place where it's pink and blue, you're slowing down.
Is there a place where?
You see what we're talking about? If you look at the pink blue regions, they're talking about velocity and acceleration. Anytime the colors are the same, you must be speeding up in that region of time. Anytime the colors are different, you must be slowing down. Okay?
Oh wait, they're the same. For what? Every time, aren't they?
What are you talking about?
These sign charts.
I don't know. What are you saying?
I'm saying that these are all lined up, zeros, wherever it's blue, wherever the pinks line up, in that region of time.
Oh,
Here to
so
here.
these are combined. Okay, I see they're separate.
Right. So right there, and here they're different, so you must be slowing down.
Okay.
Here they are the same, you must be slowing down.
Okay.
Okay?
Slowing and speed. Slowing and speedy. Okay.
All right. Let's go on. Conrad's here, he's showed up late. All right, that was fun, and perhaps the spring wasn't your best scenario. Maybe I'll go with the jetpack.
That Jim Pack while you're
Or just,
Okay,
I just sound like the Warhawks. Something's in front of me like that.
listen up, folks. Are you familiar with logistic curves?
Yeah.
Yes.
I like that. We talked about it yesterday.
Yes, sir.
Did you talk about bunnies when you talked about this?
Yes.
The Killing Bunnies in 1984, we didn't talk about that.
We're gonna talk about the bunnies again?
No, we could if you wanted to, but I'm afraid it will get you guys all riled up and not talk about calculus for bunnies, and I don't wanna do that. Okay, listen up. Look at the graph to the left on the bottom of page 210, and listen to this situation. The growth of an individual company, of a population, in sales of a new product, or of salaries often follows a logistic or life cycle curve. Not life cycle. Like the one shown in what you're looking at. I'm asking you to see it. For example, sales of a new product will generally grow slowly at first, then experience a period of rapid growth. Eventually, sales growth slows down and down again. So it continues to slow down again. The function f in this figure you're looking at is increasing all the time, right? Okay, now listen to this. You'll see this a lot. You need to make sure that you watch out for it. Hear yourself say it and think properly about it. It says, its rate of increase, oh, no, that's not the one. Never mind, I wasn't at that time yet. Its rate of increase at prime is at first increasing. The rate of increase is increasing at first. It's increasing, but the rate at which it's increasing is getting steeper. In other words, the slopes of the tangent lines are getting bigger for a while. So the rate at which the rate is changing is increasing.
Changing.
When you see rate and increase in the same statement, or rate and decrease in the same statement, you're talking second derivative, because you're talking about how the rate is changing. Watch for that, rate and increase in the same statement, or rate and decrease. Okay, listen. Shh. Up to the point of inflection, and then its rate of increase is decreasing. So the second derivative is negative, because the slopes are getting smaller at that point, after the inflection point.
So
This is in a sense the opposite of what happens in figure 4.21. Where's 4.21? 4.21 was our first encounter with this thing. 4.21 is on page 207, and that's the opposite of what's going on there. Because at first it is concave up. The one we looked at there was at first concave down. That's what it means in a sense, it's opposite. You know what I'm saying? In this logistic curve, it begins by being concave up, and then it goes to concave down as it settles on the carrying capacity. Okay? Some graphers have a logistic curve as a built-in regression model. We do. We have a logistic regression model. We use this figure in example 6. So we're talking about logistic curve here, and we're talking about the population growth in Alaska. Why Alaska? I don't know. But the data provided that was collected by the census in years since 1900, started in 1920 and went up to 2000. Those populations, the population is given to you there in the table. Notice that the populations continue to go up and up and up every year. They go, or every 10 years, they go up and up and up. But they don't go up as fast in certain regions. You with me there? It says find the logistic regression for the data. Can you do that? Do it.
Some of those over.
Yeah, that
People, please try to keep in mind this is a logistic regression, not a log regression. So don't get confused when you go to find the correct regression.
I should have just cleared before. Why didn't I do that?
bless you.
Thank you.
COVID.
That's what I was waiting for.
Did you see that meme that they had that said, I used to cough to cover a fart, now I fart to cover a cough?
That's so funny.
Y equals
Exactly.
on, where that graph, do a zoom in.
Why zoom?
Or, because I'm a cheater.
Are you lazy?
And then when it won't go to a plot.
What?
It's calculate first. Which is bars by bars.
Okay, that's.
I don't think we're doing our value for that though.
We do this, right? And then we do. That. Calc. What do you do? Calc.
I think by looking at the points that I had plotted, I think I'm gonna let my window go out quite a bit more, because it hasn't settled yet. I'll let my window go out maybe.
Oh shoot.
What are you doing? Did you store the Y one?
So bars are by function.
Did y'all find your logistic way down there at B?
Calculate.
What did you say?
Yeah.
Ooh.
Visually speaking, does it look like a good fit?
I need to make a good win.
I think it's pretty good.
0 to 120. Okay, good window is 50,000 to 700,000.
Let's use, have you guys gotten the A done? You fit the curve,
I have no idea.
and does it look like a good fit? You got something like this?
I got a good fit.
How do I get the line?
Mentioned addition that actually.
It's just taking a while.
Jose, what were we talking about yesterday?
There's a function that was
It's, there was no antiderivative.
Jose, there's a
Yeah,
function.
and then we were just like,
There is something.
Wait, Jose,
just like,
Jose,
It is,
what's the
it's
function that
that
was?
No, you got the last one in there. Figure out which one's missing. I'll show you how to
Jose,
insert
what's the function that was in there, the graph? I deleted whatever that was.
yes, oh my.
I've seen this 5 times.
I was like, what is this doing?
What is this crap?
So I'm not
Like,
gonna
Jose,
insert.
Like, look, I saw this and I was like,
Zero.
That's what you want.
Then it should work.
so it's just supposed to look like this?
Okay, so has everybody got a logistic curve that looks something sort of like that?
Yes.
Yeah? Yeah? You might want to extend your y's up and your x's out so that you can see where the thing begins to flatten.
X,
Yeah, it's
180.
It's so perfect.
Yes, Mr. James bought it for me because he could come with it.
That was a little bit too far.
I went to a million.
I know what you're saying. I didn't go.
Demonstrating-
I didn't go. Yeah, millions.
When I'm talking online and showing things.
Billion.
It's
Oh, my
very
math.
different. Much easier to say red curve and blue curve.
I already have white.
Okay.
I like the color.
Yeah. Has everybody got a log curve like that, logistic curve like that? You need to see it starting to settle. Now, the B part says, use the curve to predict Alaska's population in 2020. How are you gonna do that?
Huh, Google this.
Go down
You go seconds, count a value at 1 1.
7, 8, 1, 2, 5.
I was wrong on that.
Yep. 781,000 is what they're predicting. If it follows this curve.
Yeah, that's what she said.
Count the value. Your curve may have fit it. You might be 1 digit off on when you're that. So it's 70 something.
I'm gonna look up what they.
Okay. Shh. Or I might. Everybody's able to make the prediction on the B part, yeah? Is that true? B part says predict the population in 2020 according to this curve. We got 78,100, no, 781,000 something. 253 is what
We're
we're.
only 50,000 off.
78.
When we're talking millions, yes, that's fine. 50,000 off.
Actually, that was in 2019. That would be better.
So it's a pretty good predictor. Is it under or over? Prediction.
It's lower, but
Prediction's
that's
lower?
in 2019.
It's 53 over.
Okay,
It might be there.
okay, yeah.
Why don't you just plug in?
That's actually pretty good.
Okay, listen up. Shh. C part says, find the inflection point of the regression equation. Holy crap, how are we gonna find that?
Oh, we derived it.
Ender.
You can enter Y1 and enter Y2. It will take forever. Stop, don't do it. I want to discuss this with you first. Shh. If you have your calculator find the first derivative of this, and then you have it find the second derivative, making the first derivative of the first, every single point it plots, it has to run it through the original curve, the derivative, and the second derivative, get an XY value, and plot it. And it will take it forever. And it's, even with the CPU, you know, it's pretty powerful CPU, but even with that, it takes forever to plot the second derivative. Can you think of a better way?
I do it by hand.
Do it by hand and then we find the
Make a
second.
guess.
We find the first derivative and then enter that.
That's what I just said. It will take forever to graph that. If you
Without
have-
entering the first derivative. Without entering.
We derive the original function.
You got
Put that in Y1
Put
and
that
then
in
derive
Y1
that,
and then derive
so that it's not trying to derive from the original.
Yes.
You could do that. That's, you'd have to type in a lot of stuff and it would be an approximation.
Wait, how would
What
you do
if
that?
we use like the critical values and then we use the same way that we found the equation for that one?
Kinda. I could tell where you were going for a
Like,
second,
if we
but you
could
wandered
set
off
it.
into strange lands.
That's kind of what Jose said, isn't it? Jose said to find all the
Well, I said,
points on the derivative and put those in our stat edit, and then do that. Get a regression curve of
Sorta,
that.
I think you're kind of thinking along the lines of Jim convinced me yet.
Okay, you.
Do you think, what I wanna know is, do you think it will graph the first derivative fairly quickly? It will, because it's only got one derivative to do. Can you use the graph of that first derivative to find an inflection point?
Yes.
Yes, maximum.
Yeah. Max.
So what will it be, a max or a min?
It'll be a max. We've already decided this. It's a max.
Okay, so if we graph the first, listen, if we graph the first derivative and find the maximum of that, You're telling me that's an inflection point?
Yeah.
Yes, because that's where its derivative will be zero. Right?
That's.
So find your first derivative. How do you do it?
Math 8.
Go to y2 and do math 8.
Oh crap.
So you can graph
Third control Z.
and then put in y1, comma, x, comma, x.
Wait, what do you put? Math 8.
And then type in y1 so you don't have to type y1 is
I tried doing it in Y1. And so it messed up. Wait.
Oh, you have to
Type
search the
y1 so
window
it
again.
refers to
We're still gonna figure out how to
Anyway.
match that antiderivative.
and every x in the string.
That antiderivative, we gotta figure out what that was.
All right, so did anybody hit graph
Yes.
after doing that? And did you get anything?
Yes. You just have to adjust your window a lot.
Oh,
Yeah.
Did you get anything in the window you were using?
What?
No.
It's just like a little easy.
Why are you not getting anything in that window?
Because it's not gonna be that big.
Because the slopes are what we're graphing. The slopes are not in the hundreds of thousands like the population is. Right? So you're gonna have to adjust your window. What did you adjust it to?
I adjusted mine.
I think I'll leave the x's alone.
Yeah, X is alone. I
I put it at
Y min is what?
Y min negative 1, 1, 1, 1.
I'm gonna say, really? Negative 1, 1, 1, 1?
That's just what I did.
Okay, so negative 1,000 about then?
Yeah, negative 1,000.
And up to 1,000, will that cover it?
I did 100,000, but it's way too small still.
Remember, we're talking about slopes. Do you suppose that in a 10-year period that the average rate of change was in the thousands or tens of thousands?
Thousands.
Tens of thousands?
10,000 is good.
You want 1,000? What'd you say, 10,000?
10.
Okay,
Actually,
all right,
I don't know what I'm supposed to be looking at. Mine go over
Do 30,000.
okay.
Oh, I see a little.
Is it graphing fairly quickly or is it taking a long time?
It's taking quite a while.
It takes a while to get started.
Yeah, okay.
Oh, with my Y max at 10,000, I can't quite see it.
I did
Oh, yeah.
30,000.
Okay,
I did
all right.
1,000.
10,000 wasn't quite big enough.
I'm doing like 5.
52 million, baby.
See, this is why it's important for you to think about the window size and what we're really representing. You're representing average rates of change in population. That's on the order of tens of thousands of people. Tens of thousands wasn't quite big enough. So what is the maximum of that derivative curve?
Let's see.
Why do I have my
11,553.
first one on?
And x equals 82.75.
What did you say?
I
This.
want to know what the maximum of your derivative is.
Oh,
That's
that
going to tell us our inflection point.
Barely inside the 12,000.
It's only 500.
What does it tell you x is?
It's
80.
11,500.
X is 82.
X is 82.76, almost 83. Let's pretend it's 83. That's closer to 83. What does that mean?
In 1983 is when
In 1983,
the rate.
The rate of change was 100 or.
The rate at which the
so
rate of
let me
change.
get you started this way. In 1983, the population of Alaska
Changed
Changed.
11,553.
Increased by 11.
I agree with that number. Tell me about the population of Alaska and what you can say about population growth altogether. In 1983, the population of Alaska was
The highest.
The
most.
increase.
growing.
Fastest.
The fastest.
There we go.
That's what I was trying to get at.
Growing means a rate of change. Fastest means how fast that rate of
So
change
those
is.
builders were making some new law.
I want you to understand the language here. In 1983, the population of Alaska was growing, that refers to the first derivative. The fastest, that refers to the second derivative. Fastest, growing fastest. That's two rates. That's two ideas of rate. You understand what I'm saying? So the inflection point is located at 1983, comma, 11,553. Tell me, he spoke about it first. Tell me the significance of that 11,000. Pretend it's 12,000, so we can talk about it reasonably. What does that 12,000 mean?
People are adding that year.
Yeah.
12,000.
Yeah.
That was the rate.
At which people, the population was changing.
Fastest.
The fact
Not the fastest.
it's just
Per year.
That's the rate at which the population.
was increasing per year.
Okay,
There we
okay,
go.
all right, yeah. Tough to talk about. Okay, moving on. Let's try the D part. What does the regression equation indicate about the population of Alaska in the long run?
It'll just kind of narrow out.
In 2080.
Talk to me about numbers.
It'll just go not.
According to the graph, this is not necessarily what's going to happen in reality, but according to the graph, the population of Alaska will,
Slowly stop increasing.
The rate.
at what number?
When will it stop increasing? Never.
No. What will be the population be when it settles into its niche?
What do you mean?
When it
When does
levels
it
out,
flatten out?
or when like this, when it levels out, what will the population be? So that there's as many births as deaths and no one's coming in. That's not what's gonna happen. But what happens with this, where the population levels out, stays the same? What will that population be? Around 900,000. It's in your equation. Look in your Y1 where you put your equation of the actual function, the logistic curve. It is 895,597.8. You're crazy about it. It is the numerator. It is the numerator. That's your carrying capacity, if you'll remember from pre-calc. Remember? It's the numerator of the logistic curve equation. The numerator is the carrying capacity. Call it M. Do you remember?
Yes.
Yeah, everyone wants
It's in the equation. Okay. Last thing. I got time to tell you. What is the last thing? What's the question? Okay, example 7. Says, find the extreme values of this function. But we're going to use what's called the second derivative test for local extrema. This is not difficult, but you need to listen to the explanation. Listen. Are you listening? If the first, think about this. If the first derivative is 0, critical value, right? Pretend it's a polynomial, so we don't have to consider corners and cusps and discount and all that crap. It's a polynomial. So think of a place where this polynomial's first derivative is 0. That'll be a max or min, right?
Yeah.
So the first derivative is 0. The second derivative is positive. Will it be a max or a min?
Good, man. You said.
Why?
Second derivative theory or whatever. Well, because if it has to be.
Listen.
So say positive, negative again.
Okay.
Okay, tell me again.
The second first derivative's value is 0.
Okay.
The second derivative value at that same location is positive. Are we looking at a max or a min in the original?
Max. It's a max. Because of that.
It's max because
You're turning it like this, so it has to be a max.
Really?
It's increasing, so it's
No.
negative and positive.
No. What does it mean that the second derivative is positive? Making it a good job. Now, if the derivative of if the first derivative's value is 0, so y'all know what that means. Polynomial. First derivative's value is 0. The second derivative at that same location is negative. We're talking about a max or min in the original function.
Max.
Max, because if the second derivative is negative, it's concave down there, which means you have a max. You see? It's called the second derivative test, and that's what we're going to use in example 7. It doesn't always work. But it always works on polynomials. If you got a polynomial, if you're really good at taking derivatives, which you are, you can do the second derivative test and tell whether you have a max or min without a sign chart for the first derivative. You can do it without a sign chart if you understand how these all work. So I've got x cubed minus 12x minus 5. X cubed minus 12x minus 5. Is that what I said?
Yes.
What's the first derivative?
3x squared minus 12.
Which is 0 where?
0 at 2.
Yeah.
Plus or minus 2, because you're going to square root. Okay? Can y'all do that in your head? Solve that? So I set it equal to 0. It'll never be undefined, so these are my two critical values, yes?
Yes.
And the value of the first derivative is 0 there. What is the second derivative?
6.
What is the second derivative at 2?
12, which is positive, so we have.
Positive. That's all I'm interested in. What is the second derivative's value at negative 2?
Negative.
Negative. So, at positive 2, do I have a max or a min?
Min.
min.
Turning up.
Concave up there. Got a min.
Oh, yeah.
At -2, I have a max. Because it's concave down there. Besides the fact that this thing will start high and end low. I'm sorry, start low and end high. Which means it will have a max first. And a min second. Starts low. Ends high.
So it's negative, it's a.
Max here, min here. That's
Wait,
more verification for it. Do you understand what I'm saying to you or not? Okay.
wait, so if the second derivative is positive, then it's,
Minimum, because it's concave up there. That's what positive means. Concave up means you got
Because you're turning up.
the bottom of a dish instead of the top of a donut.
That's why when I used like why I was like, and I started to explain and I realized I was wrong. I couldn't figure out why I was wrong. I was like, I'm confused.
All right, let's see. So that's called the second derivative test for max and min. You can use it on polynomials. Doesn't work on hardly anything else, but it's nice for that. Most interesting thing is that you already know the behavior of this graph if you remember your pre-calc well enough, so you really don't need this. You know you're going to encounter, if it's going to start low and then high, you're going to encounter a max first and a min second.
Yeah, I don't trust myself with that.
Okay, that's fine. This will
I feel like
verify
maybe it's
for you.
reflected.
And if you must use calculus to get 100% on the question you're being asked, then this is nice rather than what you learned in pre-calc. All right, so take a look at example. It says the first derivative is 4x cubed minus 12x squared. This is our goal. Identify where the extrema of f occur. Find the intervals on which f is increasing and the intervals on which it is decreasing. Find where the graph of f is concave up and where it is concave down. And sketch a possible graph for it. That's a tall order, folks. And it gave us the first derivative, which is 4x cubed minus 12x squared.
What is the arrow?
plus the.
This is not necessarily off topic. The arrow that looks like this.
Means implies. It's a verb. It's either you can replace it with the word implies or you can replace it with the word means. This means this or this implies this.
Okay.
Okay. That's a logic symbol.
Oh.
If you put it on both ends, it means it's biconditional. One can apply the other, and the second one can apply the first. Okay. All right. So f prime is 4x cubed minus 12x squared. What's our first task? Find what? Well, that is exactly what it says. What does it say? What does the A part say?
Find the critical point.
Find extreme values, which means setting it equal to 0, since it'll never be undefined, right? Where will it be 0?
X
minus 3.
So 3 and 0.
So the zeros occur at
3 and
0. This is very important.
Plus or minus 0.
No, just listen. Multiplicity 2 shows up twice. And 3. Now, do you remember the behavior of a graph when the multiplicity is even?
It has like
touches.
It bounces off, right? Yeah, it bounces off of the x-axis at 0. What does that mean? What does that mean in the context of this problem? When it bounces off, it means your first derivative has a shelf because there's no sign change there. Because it bounced off. It stayed positive to the left and it went positive to the right. We're still going to do a sign chart, but I want you to expect that because multiplicity 2 means bounces off, no sign change, remains positive or negative, where however the bouncing happens. But still, the sign chart for finding critical values has a 0 and a 3 on it. To the left of 0 is the derivative, positive or negative. Let me tell you how a quick way to do this. This term will always be positive no matter what, right? So it's going to be a positive times. To the left of 0, it will be negative 2 minus 3 is negative, right? So it is negative, which means decreasing. Okay, between 0 and 3, consider a 1. This will be positive all the time. Will that be positive or negative? Negative. So it is decreasing. Shelf point. To the right of 3, this will be positive, times this will be positive. So it's increasing. Making this a
Max, so minimum is, yeah, minimum.
Changes from negative to positive is,
Oh boy, are we slow.
this is how we identify these to be, right? Besides that, a cube function with a positive leading coefficient starts low, ends high.
My simplicity.
There's your bouncer at 0. Stays negative in both cases, right? Okay, these are, by the way, these are comments about the original function, which we don't have. We have the derivative. We don't have the original function. These are behaviors of the original function, this. And these, shelving and miniming. You with me? Okay. All right, so let's take the second derivative and see what, well, first of all, these are the answers to the A part. What's the B part say?
I don't know.
Find what? Increasing or decreasing, well, actually, this is A and B then. Because we identified increasing and
So
decreasing,
cool.
Is that
right?
Concave up, concave down.
F with X?
What?
Is it A and B for F?
No, this, right, behaviors of the original function f, which we don't have, okay? The original function is decreasing to the left of 0. It continues to decrease between 0 and 3. Then it begins to increase after 3. But vertically, we have no idea about its location. This was a picture of our derivative. Don't look at that.
Okay, that's right.
Yeah, right, sorry, I made a confusion.
Oh.
So B has been answered because we answered that as we did the sign chart. How about C? What do they want to know in C?
Concave up, concave down.
What do we need?
Second derivative.
Second derivative. F double prime is equal to 12x squared
Minus 24x.
minus 24x.
X minus 2.
What?
You can simplify 12x, x minus 2.
So 12x, x minus 2, because we're attempting to set it equal to 0, it'll never be undefined, and so the zeros are 0 multiplicity 1 this time, and 2. So we put a sign chart for the second derivative with a 0 and a 2. Right here in this region, second derivative, this is going to be negative times a negative. Negative 1 minus 2 is still negative, right? Which means it is
Positive. I mean,
positive, which means in the second derivative it is
Increasing.
concave up. Increasing and decreasing was first derivative. Gotta keep straight what we're doing. Between 0 and 2, like a 1. That will be positive, this will be
Concave down.
concave down. And here,
Concave
Positive?
up.
positive, right?
yes.
Concave up. Okay, so we've got some things to do here. Now, I mean, we've got some information here.
And is that of, that's of F, whatever F function is.
This is of this.
This is of the original function. These are descriptors for the original function, which indeed, now they want us to graph. Is that right?
Yes, they do.
Now, can we graph it from this information? We cannot locate it vertically properly. We cannot do that. So I'm just going to draw a y-axis so we've got some reference, but we don't have to locate it vertically in any particular place. What would you like to put on the x-axis?
I would like to put those numbers.
So 0, 2, and 3.
0, 2, and yes.
Okay.
0.
We got 0 here, 2, and 3. We need to sketch the original graph. We don't need to do it vertically properly. We can't do it vertically properly because we don't know what the C value is. What are we going to have to do? Starting to the left of 0, what's it going to be doing?
Decreasing.
It's going to be coming down and be
Concave up. So
Concave up.
like this.
like this.
Well, that is so easy.
Yeah, it isn't too bad once you have this information. Between 0 and 2, what's it going to be doing?
Decreasing, concave down. So
Coming down and concave down. There's our shelf point right there. There's your concave down.
now
What's it going to be doing between 2 and 3?
increasing, concave up. So
Increasing and concave up.
no, I don't know why. It says increasing.
No, it says decreasing
Wait.
from 0 to 2
But
is
3 is
decreasing
the
still.
base.
Oh,
There's a minute.
oh.
What?
0 to 2 is still decreasing, yeah.
What about 0 to 3? It's still decreasing. 0 to 3.
Oh, 0 to 3 is decreasing the concavity.
It's probably
Yeah.
decreasing less. So it goes.
Yeah, how are we going to account for that? Still decreasing clear to 3, and then it increases.
By-
Straight line.
by less.
Just y equals x.
So you need it to still go down
Two,
just
it
by
starts
less.
becoming concave
Becoming concave up is still going down.
And then it changes to going up at 3. So lessen the amount of down, and then turn it up.
Yeah, like that.
Perfect.
Pretty crappy.
I'm a fan.
Okay,
100%.
now uncover the post-it, see if we got something kind of like that. I mean, mine's not like theirs. Notice they did not put a y-axis on it either. Perhaps we should do that. That's kind of what we have, right? So you're able to put a graph together. If you can get this information, make things happen that way. It's not too bad.
That's what we're gonna do on the test.
Exploration 1 talks about finding f from f prime. Take the same f prime we just had. How do you find that?
Isn't that what? I don't know.
How could we find f if we know f prime here algebraically?
Anti-derived.
Okay.
X to the 4.
What will be the exponent on this term?
4.
The X 3.
So this is 1 because when you multiply 4 times 1, you get the 4x to the third. So this is the first term. Then what's this one?
Minus
6.
It'll be x cubed.
4x
It'll have to be a 4 here, right?
Plus
So
C.
you get a 12. Don't forget your plus c.
Remember the C.
That graph right there should be something like this. Even if you let c be 0, it should look something like that.
That doesn't look like a cool board.
It's not too hard. But I want you to be able to start at f prime and draw a graph of f. Okay, I mean, you now have the entire lecture, so the entire assignment is now your job. Get after it.
Do you have a class next hour?
See ya.
What?
I do.
What class?